Hey guys, today we're going to learn about theorems regarding polynomials and their zeros. So the first theorem listed here is the fundamental theorem of algebra, which is one that we've already covered. If a polynomial has a degree of n, then it's going to have exactly n zeros or roots. So if the degree of a polynomial is 3, then you're going to have exactly 3 zeros. Whether those zeros are rational numbers, such as 1, 2, 3, 4, 5, etc., irrational, meaning, let's say, like the square root of 3, or complex zeros, such as 2 plus I. So no matter what the case may be, whatever the degree is, that's exactly how many zeros you're going to have. The next theorem is the conjugate root theorem. And what this is that when a polynomial equation in one variable with real coefficients has a root of the form a plus bi, then its complex conjugate, a minus bi, will also be a root. So as examples, if you have, let's say, you know that 2 plus 3i is a root, then the conjugate 2 minus 3i must also be a root of that particular polynomial. And this also applies to irrational roots, such as radicals. So if, let's say, 2 plus the square root of 3 is a root of your polynomial, then its conjugate, 2 minus the square root of 3, will also be a root. The final theorem we're going to discuss is the linear factorization theorem. And what this is if f of x is a polynomial function of degree n, then f of x has exactly n factors, which include real, complex, and repeated zeros. So, for example, if, like, very similar to fundamental theorem of algebra, if the degree is 3, then you're going to have exactly 3 factors for that polynomial. Now notice that the name of this theorem is linear factorization. That means that every particular factor will have x with no exponent, because if it's, let's say, x squared, then that's not a linear factor. A linear factor is where the exponent of x is 1. So I put here as an example, which is something that we've kind of been working with when we were dividing. If a polynomial f of x has the roots 2, -3, and 4, then according to the linear factorization theorem, the factors would be x minus 2, x plus 3, and x minus 4. So remember how we get our roots, our factors from the roots. If x equals 2 is a root, then to get the factor, we would make it equal to 0. So I would subtract the 2. And we get here the x minus 2. The same thing, if x equals -3, we would have to add the 3, giving me x plus 4, etc. So now, how are we going to apply these particular theorems? First, let's work with the conjugate root theorem. Write a polynomial function of least degree with real coefficients in standard form that has the roots -2, 4, and 3 minus I, and that satisfies the condition where f of 1 is equal to 90. We'll get to this part later, but first of all, if I have that these are my roots, first of all, we are also told that 3 minus I is a root, and even though it's not listed here, because of the conjugate root theorem, we know that 3 plus I must also be a root. So how are we going to write out this polynomial? If -2 is a root, then that means that x plus 2 is the associated factor. Anytime you put a number into its factored form, remember that you have to change the sign because you're moving it across the equal sign. So again, here this is x equals -2. We would have to add the 2 to both sides, and we get the factor x plus 2. If x equals 4, then I would have to subtract the 4 to both sides to get the factor, which is x minus 4. Now we're going to do the same thing with our complex numbers here. If x equals 3 minus I, then I would have to subtract the 3 and add the I. So my factor would be x minus 3 plus I. Then for 3 plus I, if x equals 3 plus I would have to subtract the 3 and then subtract the I. So I get the factor x minus 3i minus, x minus 3 minus I. So here we have our linear factorization of that particular polynomial. However, the question is asking for this polynomial in standard form. So if we want it in standard form, we're going to have to multiply everything out. Now, remember, we can only multiply two things at a time. So since I have 4 factors, I'm going to multiply these two together and then these two together. So x plus 2 times x minus 4, we will get x squared minus 4x plus 2x minus 8. Now I chose, and I'm always going to do this, I'm always going to multiply those conjugates together. Okay, so the order in which you multiply does not necessarily matter. However, if I multiply, let's say, x minus 4 with x minus 3 plus I, not that it's wrong, you can multiply these two if you want first, for whatever reason, but you're going to have I within your polynomial until you multiply the conjugate. If I multiply the conjugates together first, once I simplify that, you're going to see that you're going to have no more complex numbers, no more imaginary numbers. So that's why I always choose to multiply these two together at the beginning. So when I distribute, I'm going to distribute the x first. X times x is x squared. X times negative 3 is negative 3x. X times negative I is negative ix. Now I'm going to distribute the negative 3. Negative 3 times x is negative 3x. Negative 3 times negative 3 is plus 9. And negative 3 times negative I is plus 3i. Finally, I'm going to distribute the I. I times x is plus ix. I times negative 3 is negative 3i. And I times negative I is negative I squared. Now before I go ahead and distribute all of this now, I'm going to go ahead and simplify each of these factors. So here I can combine these two like terms. So x squared, negative 4x plus 2x is negative 2x minus 8. Now over here, let's look at what happens. I have the x squared. Then I have negative 3x minus 3x, and that's it, so minus 6x. Now let's look at the ix's. I have a negative ix here and a positive ix, so these will cancel. Then I have this 3i and this negative 3i, these will also cancel. And we know that negative I squared is going to end up being positive 1. Since I squared is negative 1 and the negative in the front, a negative negative makes it positive. So I can combine the 9 plus 1, which is plus 10. And you see now in this factor here, we no longer have any i's. Now we're going to go ahead and distribute this to get our final polynomial. So x squared times x squared is x to the 4th. X squared times negative 6x is negative 6x to the 3rd. X squared times 10 is plus 10x squared. Now distributing the negative 2x. Negative 2x times x squared is negative 2x to the 3rd. Negative 2x times negative 6x is a positive 12x squared. And negative 2x times 10 is negative 20x. Finally, we're going to distribute the negative 8. Negative 8 times x squared is negative 8x squared. Negative 8 times negative 6x is a positive 48x. And negative 8 times 10 is negative 80. Combining like terms, we get here x to the 4th. We have negative 6x to the 3rd minus 2x to the 3rd is negative 8x to the third. And I like to scratch things off as I use them so I can see what's left. Now all of the x squared. We have here 10x squared plus 12x squared, which is 22x squared, minus 8x squared. That's going to be plus 14x squared. Now all of our x's. Negative 20x plus 48x is plus 28x. And finally, our constant, minus 80. So this is our polynomial given these zeros. Now the only additional thing is that here we want this polynomial to satisfy the condition that f of 1 is equal to 90. Now you can certainly plug in 1 into every x, or I put here, if you want to make it a little bit easier, I mean 1 is not that hard to plug in, but in the future, to find the function value, you can use direct substitution, which is what I just said. We can plug in 1 for every x, or we can use the remainder theorem. So remember that the remainder theorem, or another term, synthetic substitution, also gives us the function value. So we want to check, will this equal to 90? Because that is what we want our polynomial to equal to. So I'm going to go ahead and use synthetic substitution. So I'm going to put 1 in the box, and I'm going to write all of my coefficients. 1, negative 8, 14, 28, and negative 80. Bring down the 1. 1 times 1 is 1. Negative 8 plus 1 is negative 7. Negative 7 times 1 is negative 7. 14 minus 7 is 7. Times 1, 7. 28 plus 7 is 35. 35 times 1 is 35, and negative 80 plus 35 is 45. Negative 45. Now what we wanted is for this polynomial to equal to 90. But here we get that f of 1 is equal to negative 45. So our zeros are fine. We did all of this correct. The only thing is now that we want our function value to be that 90. So once we get our function value, if it doesn't equal to what we need it to equal to, we have to figure out what number we need to multiply in order for this negative 45 to become 90. In order for this to become 90, we would need to multiply it by negative 2, since negative 45 times negative 2 gives me 90. So what I'm going to do with this number is I'm going to take my function, my f of x, and I'm going to multiply it with negative 2. So I'm going to take all of that there that I got. Remember that this is just a coefficient or a number that's being multiplied. It's not going to affect our zeros since there's no x attached to it. So if I take my polynomial and I multiply it with that negative 2, then if I were to do synthetic substitution again, or if I plug in the 1, then my f of 1 will in fact equal to 90. So I'm going to distribute the negative 2, which would give me my final polynomial function. Negative 2 times x to the fourth is negative 2x to the fourth. Negative 2 times negative 8x to the third is plus 16x to the third. Negative 2 times 14x squared is negative 28x squared. Negative 2 times 28 is negative 56x. And negative 2 times negative 80 is plus 160. So this is my final polynomial function. Let's try another one. Write a polynomial function of least degree with real coefficients in standard form with the zeros negative 1, 1, which has a multiplicity of 2, and 4i, and that satisfies the condition where f of 2 is equal to 60. So first we need to write out our linear factorization. Since I know that 4i is a root, negative 4i is also going to be a root. So our polynomial, if negative 1 is a root, in order to turn it into our factor, we would need to make x equal negative 1 equal to 0. So I would have to add the 1. So my factor would be x plus 1. Then if x equals 1, I would have to subtract 1 in order to make this equal to 0, so x minus 1. Since it has a multiplicity of 2, then that means that there's 2 factors of x minus 1. And if 4i is a root, then that means that the factor x minus 4i is a root. And if negative 4i is a root, then x plus 4i is also a root. So these are all of my linear factors. Now I have to start multiplying everything out. And I like to multiply 2 at a time. So I'm going to multiply these 2 together. And I like to multiply my conjugates together. So I'm going to multiply these 2 while I do these 2 as well. So let's see how that's going to work out. X times x is x squared. X times negative 1 is negative x. 1 times x is plus x. And 1 times negative 1 is negative 1. I'm not working with this x minus 1 yet. And now over here with our conjugates, x times x is x squared. X times 4i is plus 4ix. Negative 4i times x is a negative 4ix. And negative 4i times 4i is negative 16i squared. Let's simplify these factors a little bit. Here, my x's will cancel, and I get x squared minus 1 times x minus 1 times x squared. These middle terms here cancel out, and this negative 16i squared is negative 16 times negative 1, which becomes plus 16. So this is x squared plus 16. Now I'm going to go ahead and multiply these 2 together. X squared times x is x to the third. X squared times negative 1 is negative x squared. Negative 1 times x is negative x. And negative 1 times negative 1 is plus 1. I have nothing to combine there since they're all different terms, so now I'm ready to multiply my final factors. X to the third times x squared is x to the fifth. X to the third times 16 is plus 16 x to the third. Now I'm going to distribute the negative x squared. Negative x squared times x is negative x to the fourth. And negative x squared times 16 is negative 16 x squared. Now when we distribute the negative x times x squared is negative x to the third. Negative x times 16 is negative 16x. And finally, distributing the 1, that's going to be plus x squared plus 16. So now let's combine like terms and write our polynomial in standard form, starting with our highest exponent, which is x to the fifth. Then I have minus x to the fourth. Now our x to the third, we have 16x to the third minus x to the third, which is plus 15x to the third. And then negative x squared plus x squared is minus 15x squared. Then minus 16x plus 16. So far this is my polynomial, but it has to satisfy the condition that f of 2 is equal to 60. So I'm going to use my synthetic substitution to check if it equals to 60 or if I need to multiply my polynomial by some number. So I'm going to write out my coefficients: 1, negative 1, 15, negative 15, negative 16, and 16. Bring down the 1. 1 times 2 is 2. Negative 1 plus 2 is 1. 1 times 2, 2. 15 plus 2 is 17. 17 times 2 is 34. Negative 15 plus 34 is 19. 19 times 2 is 38. 38, or negative 16 plus 38 is 22. 22 times 2 is 44. And 16 plus 44 is 60. And we get here that it does already equal to 60. So we do not need to multiply this polynomial by any coefficient. So this is my final answer. Now, how do we use the conjugate theorem in order to find the zeros of a polynomial when we already know that 1 is a zero? So if I have here this particular polynomial, x to the fourth minus 5x to the third plus 15x squared minus 5x minus 26, given that 2 minus 3i is a zero of p of x, then we're going to write the linear factorization of p of x. So if I know that this is a root, then I also know that 2 plus 3i is also a root. Now this is something that we've already done in our previous lesson, but now we're going to do it with complex numbers. If you have a root and you want to completely factor your polynomial, we normally divide that root from the polynomial. So I'm going to start with 2 minus 3i. That is my root, and that is what's going to go inside of my box. It's going to look really weird at first. So the beginning is always the hardest part, and then it'll get easier. So I'm going to write out my coefficients. I'm not missing any terms. So 1, negative 5, 15, negative 5, negative 26. I'm going to bring down the 1. 1 times 2 minus 3i is 2 minus 3i. Now I combine these. I can only combine the real parts. Negative 5 plus 2 is negative 3, and then we have the imaginary part, which is minus 3i. Now I need to multiply this with what's in the box. So I'm going to do that here off to the side. I need to do negative 3 minus 3i times 2 minus 3i. When we distribute the negative 3, we would get negative 6 plus 9i minus 6i plus 9i squared. Here, this 9i squared becomes minus 9, and I can combine my like terms now. Negative 6 minus 9 is negative 15, and 9i minus 6i is plus 3i. So this is now what I'm going to put here, negative 15 plus 3i. When I combine 15 minus 15 plus 3i, the 15s will cancel, and I can bring down the 3i. Now I multiply 3i times 2 minus 3i. Distribute, and we get here 6i minus 9i squared. And this 9i squared becomes plus 9. So my complex number is 9 plus 6i. Combine the real parts. Negative 5 plus 9 is 4 plus 6i. Now I need to multiply one final time. 2 minus 3i times 4 plus 6i. 2 times 4 is 8. 2 times 6i is plus 12i. Negative 3i plus 4 is negative 12i. And negative 3i plus 6i is negative 18i squared, which this negative 18i squared becomes plus 18. And here my 12i's cancel, and 8 plus 18 is equal to 26. And see here, I end up with a remainder of 0. Now for the next part, I knew this would happen because I was told that 2 minus 3i is a root. But now I need to also divide 2 plus 3i. Instead of starting over with our original polynomial, then it's not going to help us because we're always just dividing from the original. We're not reducing that polynomial to its other parts. So what we're going to do now is we're going to put that 2 plus 3i in the box. And then here going across, instead of using my original coefficients, I'm going to use the new ones. Since remember, whenever you do synthetic division, you are getting a depressed polynomial. So we want to divide again using the new coefficients. So I'm going to put here 1, -3 minus 3i, 3i, and 4 plus 6i. Now this round of division is actually going to be a whole lot easier, and you're going to see why. I bring down the 1. 1 times 2 plus 3i is 2 plus 3i. And if you did this correctly, what's always going to happen is that these imaginary numbers will end up canceling. See, we had -3i plus 3i, those cancel out. And so now we only have to add the real numbers. So -3 plus 2 is -1. And now we multiply. -1 times 2 plus 3i is -2 minus 3i. And see again, these 3 i's, they cancel. And we're left with just the real number, -2. Now we multiply. -2 times 2 plus 3i is -4 minus 6i. And see, here everything should cancel because again, that is a root. So you should always end up with a remainder of 0. Now what we have here, if we started with to the 4th, then this is to the 3rd, and so this here would start with x squared. So my polynomial has been reduced to x squared minus x minus 2, which is a quadratic that I can factor. The two numbers that would multiply to give me -2 and add to give me -1 would be x minus 2, x plus 1. So these are my other two factors. But we want to write the linear factorization of the entire polynomial. So p of x is going to equal to what we got, x minus 2 times x plus 1. And then my other two factors are my complex numbers here. So if x, let's do this in a different color to distinguish the difference. If x equals 2 minus 3i is a root, then I would have to subtract the 2, so x minus 2 equals -3i, and then add the 3i, so x minus 2 plus 3i is my factor. And if I do the same thing with 2 plus 3i, I would still have to subtract the 2, so x minus 2 equals 3i, and then subtract the 3i, so x minus 2 minus 3i is my other root, so my other factor. So here, to complete my linear factorization, I use the x minus 2 plus 3i and the x minus 2 minus 3i. And notice with our complex numbers, it's just all of these, when you put them in factor form, they switch signs. So this is +2, +3i, so x minus 2 minus 3i. 2 minus 3i would be x minus 2 plus 3i, if you don't want to go through this whole process. So this would be my linear factorization. And that is the conjugate root theorem and linear factorization.